Alright, in today's video, we want to use the principle of mathematical induction to prove this mathematical statement. That is, let Sn be the sum of the n term of the series proved by the principle of mathematical induction that the series is equal to Sn. So now let's make the proof. Now, the first thing we need to realize is that the series is an arithmetic series. That is, the first term is 5, obviously. The common difference is 10 minus 5, and that is 5. And the last term is 5n. So this is the last term. This is the first term. And the common difference is also 5. So since this series contains the first term and the last term, so we can use this formula to find the sum of the n term of the series, so which is a plus the last term. So consequently, we have n over 2. Our a is 5 plus the last term is 5n, which can be reduced further to 5 over 2, because we factorize 5n, we do have n plus 1. So that being said, so now we can then begin the proof. Let the mathematical statement Pn be the mathematical statement. Okay, that is Pn is equal to 5 plus 10 plus 15 and so on. 5n is equal to the Sn. The Sn is 5 over 2n plus 1. Then we begin the proof. So we say when n is equal to 1, so we have P1 on the left hand side. So the left hand side is talking about this, so I'm going to categorize this as the left hand side. The left hand side. Then I'll categorize this as the right hand side. Okay, so as the right hand side, that implies that the left hand side, which is when n is 1, we're just talking about the first term, and that is going to be 5. So we want to ask, is it equal? That's the question. Is it equal to the right hand side? Okay, is it equal to the right hand side? And the right hand side is basically, we just substitute the value of n as 1. So we have 5 over 2 times 1, 1 plus 1. So we have 1 plus 1 is actually 2. So these two cancel out these two. We have 5 times 1. Again, that's 5. Yes, it is true. This is true. This is true. So the left hand side is equal to the right hand side. This is true. So we can make our general statement, that is, for when n is equal to k, so where k is an element of the natural number, so it is true for when n equals to k, that is pk 5 plus 10 plus 15 and so on to 5k is equal to 5 over 2k k plus 1. So we assume that this is true. Now the next thing we have to do again now is that we have to now ask, is also true for when n is equal to k plus 1. This is now the ultimate proof, we have to prove that is it also true for when n equals to k plus 1. So all we need to show, is that from the right hand side of this, we just need to show that the right hand side is equal to when n is equal to k plus 1. And you know that that's going to be 5 over 2 k plus 1 bracket k plus 1 plus 1. All we need to do is just that we substitute the value of k n as k plus 1. So we have 5 over 2 k plus 1 k plus 1. So that's all we need to show. That's all we need to show on the right hand side. So now what is the implication of this? The implication of this is this. We pick it up from here. So we remember that since this is true, we can say that our 5 plus 10 plus 15 plus and so on 5k plus when n is k plus 1, so we have this as 5k plus 1 is equal to 5 over 2k k plus 1 plus 5k plus 1, because that's the next term when it stops at n. So the next is going to be n plus 1, or we use k plus 1 depending on what the variable you want to use. So here we're using k plus 1. So we can only concentrate on the right hand side of this and show that this can be reduced to this. If we can show that the right hand side of this equation aesthetic is this, then that completes the proof. So now let's look at this. So we have this is equal to, now k plus 1 is common to all sides and 5 is common to all sides. So we can factorize the 5 and the k plus 1. So we are left with what? K over 2 plus 1. Okay, so this can be further reduced to k plus 2 over 2 because we find the LCM and the likes. So now, of course, this 2 can be seen as 5 over 2 here because that's 1 over 2. Then we have k plus 1 plus 1 because this 2 has been written as 1 plus 1. Then that completes the proof because we have shown that the right hand side of this statement has been shown that is equivalent to this, or is shown that the right hand is equal to this. So that completes the proof. So we have used the principle of mathematical induction to prove this statement. So thank you.